So this talk is about, it's actually an old talk, an old work. It was presented actually 10 years ago at AAAI. So I will talk about that, but I will also mention some updates about things that happened since. The work is about a proof-producing CSP solver. The developer of this CSP solver is Michael Wexler, my former PhD student, who is one of the attendees now, so he will also be able to answer questions. So it was presented, as I said, at AAAI 2010, and later it was also, I presented it in a workshop called CSP SAT, which focused on the relationship between CSP and SAT. I think this workshop doesn't exist anymore. And the idea, so as you probably all of you know, the world of CSP and the world of SAT are progressing somewhat in parallel, but all the time people are borrowing ideas from the other community. And at the time that this solver was developed, which was 2008, 9, something like this, there was huge progress in SAT solving. Actually, this huge progress has not stopped since. I attended SAT this year, and it's just incredible how SAT solvers are becoming more powerful every year. And at the time, the idea of Michael that I mentioned was that let's build a CSP solver basically ground up from scratch, that it will be as close as possible to the architecture of a modern CDCL SAT solver. And the result of this was the CP solver called PCS, for Proof Constraint Solver, and later the name has changed to HCSP for Haifa Constraint Solver, for Haifa CSP solver, I guess. And one of the features of this solver, in addition to the fact that it's a very efficient one, it is also able to give the same type of services that SAT solvers do, meaning that it's able to produce a machine checkable proof, as well as finding an unsatisfiable core, and other things that I will mention, like finding interpolants and things like that. So let me give you some background on the need. So we all know that once we have a solution to a CSP, it's very easy to validate the solution, just checking whether the solution satisfies the constraints. But once we get an unsat result, we're kind of stuck. We don't know whether to believe it or not. And the way to solve this problem is by making your solver produce a checkable proof. And this is what our solver PCS does. In addition to the fact that it produces a proof, it also gives us an initial unsatisfiable core, which is a good one. It's a relatively small one. Okay, it's just the core that was used in the actual proof. This is something which is completely obvious in the SAT world, but until the development of this CSP solver, this was not obvious in the CSP world. Well, and these type of things, proofs and cores, were kind of like pivotal in a sense in the SAT world. There were many applications of these things, and the hope is that maybe it will it will lead to other developments in the CSP world that resemble to what happens in the SAT world. So I will just mention several usages of proofs and cores in the world of SAT. Well, the obvious one is just to validate your unsat result, but the proof itself has been used. The proof that SAT solvers produce has been used in several applications. I'll just mention several of them. So some of you might remember that there was time, we're talking about 17 years ago, a method that was suggested by Ken McMillan back then about interpolation-based model checking, which is basically based on analyzing the resolution proof that the SAT solver produces and using this interpolant as part of a bigger loop with which you can actually do model checking. Some examples of usage of the unsat core. Well, again, Macmillan, that's a work by Amla and Macmillan from the same year of abstraction refinement in model checking. There, the idea is that you model check an abstract model where many of the latches are replaced with free inputs. You get an abstract counter example, say of length 10. Then you just use a bounded model checker, which is a SAT-based technology, to check whether there exists a proof of length 10. And the point is that if the answer is no, if the formula is unsatisfiable, you actually analyze the core of the proof in order to know how to refine your abstract model in the next step. So this is something very typical in the formal verification world, where SAT is just a component in a much bigger system. So these type of services, like producing a proof and producing a core, are used by these wrapping systems, the systems that wrap the SAT solver. I'm less aware of such bigger systems in the CSP world, but I'm sure that either they exist or should exist. Perhaps I'll mention one more work that used the core, the one that is listed here, the last one, faster solving of bit vector formulas. So this, for example, is a work that you start trying to satisfy a bit vector formula, but the original width of these bit vectors, suppose it's 64 bits, your solver is unable to solve it. So one thing you can do is you can under-approximate by restricting the number of bits. Say instead of 64 bits, start with 2 bits, and like force everything else to be 0. Now, if you're lucky, then you find a solution like this. But if you're unlucky, you get unsat. But then again, you can analyze the core and see which bits participated in the proof of unsatisfiability. And you take those bits and then you refine. You make available more bits in your original bit vectors and try again. So this way you gradually make it bigger, and if you're lucky, you're able to find a solution before you reach the entire sequence of 64 bits. So these are just some of the many usages that were suggested through the years of the unsatisfiable core. And the main question here is, can we foresee usage of proofs in CSP? I think so. I actually made a short search this morning to see whether people are using it. I have to say that I did not find anything in particular, but maybe this will change in the end. Maybe more people will be available of this, will be aware of this technique. Maybe this will steer some usage. So what is a proof? Well, a proof is, you can think of it as just as a DAG, where the roots are your original constraints, not necessarily all of them, it can be some of them. The sync node is bottom, this represents false, and everything in between are constraints that were derived from their parents. So if each step here is justified by a sound inference rule, then this is a formal proof, okay? And it's also machine checkable, okay? So this is what we aspire to. In an inference rule, what takes us from step I to step I+1 looks like this. So everybody who took a logic course knows these things. So you have the premises, things that you already established, or maybe it's the original constraints. This is what appears on the top part of the line. And at the bottom part, you have the consequent. This is the new thing that you can infer from the premises on the top. And then on the right-hand side, you usually write the rule name. So once you have such inference rules and you prove their soundness offline, like once and for all, then you can derive such proofs. So SAT solvers generate proofs from the initial clauses to the empty clause. The empty clause is basically the equivalent of false. And they use a single inference rule, which is called the binary resolution rule. But unlike SAT, in CSP, we have to deal with non-Boolean domains, and we have to deal with non-clausal constraints. So we cannot just apply the binary resolution rule, obviously. So the question is whether this gap can be bridged. So this talk is basically how PCS bridges, creates this bridge in a sense, or overcome this gap. So we'll start with some notations. We'll talk about sign CNF because this is the underlying representation that drives these proofs. So sign CNF is a disjunction of signed literals. And what is a signed literal? Well, you have either a positive signed literal or a negative signed literal, and the meaning is quite clear from the context. So a positive literal just says that one variable is in a domain, and a negative signed literal means that it's outside of the domain that is specified. Like here, for example, A cannot be 4. And a signed clause is simply a disjunction of these signed literals, like the example that appears here at the bottom of the screen. Okay, once we have signed clauses, we can use the signed resolution rule. The signed resolution rule is a very natural extension of the binary resolution rule from propositional logic, which basically says, well, you can see what it says here. So suppose that we have a variable with 2 different constraints on its domain, A and B. And once we do the resolution, we see that the consequent is, well, like in normal resolution, literals 1. Literals 1, just think about this as just a disjunction of literals. So literals 1 or literals 2, or this joint variable has to be in the intersection of these 2 domains. Okay, this is a very natural extension of resolution. So this rule can be used with constraints given as signed clauses. But this still doesn't tell us what do we do in the presence of other type of constraints, right? Because we all know that constraints can be weird and general. You have like all different constraints and less equal and whatever. So the question is, how do we actually bridge this gap? And before we do this, we can ask, well, why not just convert all the original constraints into signed clauses to begin with? And the answer to this is that this is a very ineffective way to solve the problem. So for example, suppose that you have a constraint x different than y, and your domain is 1 to 100, say, then in order to replicate this constraint, or to formulate this constraint with signed clauses, you will need 100 such clauses. Like either x is not equal to 1 or y is not equal to 1, and so forth, 100 times. So this is a very ineffective representation. So the idea is that no, we will still reason with the original high-level constraints, but only lazily introduce those signed clauses in order to create the proof, which eventually will be based on signed resolution. So we want to introduce these clauses lazily. So how do we do this? So consider a general constraint C, whatever this constraint might be, and think about the state of the solver where you have several literals, L1 to Ln. And in this context, the constraint C implies a new literal L. So this is what you see here. So the conjunction of those L's and C, L was implied. Okay. We want to replace C. Remember that C is a general constraint. We want to replace C with a signed clause. Okay. So how are we going to do this? We're going to introduce something which we called an explanation clause, denoted by E. So E has 2 properties. First of all, it is implied by the original constraint, and this is why we know it is sound. And it is strong enough to also imply L in the context of the other literals. Okay, so look at this slide for a minute to understand what an explanation clause is. Okay, by the way, if you have questions, feel free to interfere in the middle. Okay, so we have, so this is an explanation clause, E. So let's see some examples of such clauses. How do we derive such clauses? So, well, actually, just a second before we will see them, let's see the general structure of the proof once we have these explanation clauses. So think of the roots. The roots are those nodes at the top of the diagram. These are the original constraints. The proof is going to look like this. From each such constraint that participated in deriving false, we're going to derive from it those explanation clauses. Those explanation clauses are implied logically. They're actually they're sound. It's a sound implication from those constraints to these explanation clauses. And from there on, it's going to be a signed resolution proof. Okay, so this is how the proof is going to look like. And the idea is that for every constraint, there is such an explanation clause. And when I say for every clause, we actually have a proof of this. We show that basically every constraint that satisfies certain conditions and all the constraints that we're aware of that are being used in CSP satisfy these conditions, you can always come up with a recipe on how to create this explanation clause. So it's time for examples. So suppose your constraint is x different than y. So this is a parameterized inference rule. Okay, it's parameterized by a constant m. So I hope it's not hard to see that this inference is sound for every m. Okay, for example, take m equal to 7. So clearly, the consequent cannot be false if the premise is true. Because if the consequent is false, it means that x is equal to 7 and y is equal to 7. But if both of them are equal to 7, then it means that the premise does not hold, right? So this inference is sound for every value of m. So we don't have to worry about using this rule, okay? Let's see how we use this. So suppose that we have x equal to 1. This is, I hope, by the way, that you see my mouse. So we have the first literal x equal to 1, and the second literal that y belongs to the domain 1 to 100. And we have the constraint x different than y. And these three things together implied that y has to go down by 1 in its domain. So the value 1 is no longer a valid value for y, right? I think it's not that hard to see, because if x is equal to 1 and y has to be different than x, then clearly y cannot be equal to 1. Therefore, y is equal to 2 to 100. However, we used a general constraint, x different than y. And what we want to do is to replace this with an explanation clause. So what is the explanation clause going to be? The explanation clause is going to be an instantiation of the rule that we saw in the previous slide. In this case, we instantiate it with the constant 1. X different than 1 or y is different than 1. And let's see that indeed it satisfies the requirements of an explanation clause. Well, first of all, clearly it is implied by C, because all the instantiations of this rule are implied by C. So we don't have to worry there. And the second thing is that E is strong enough to imply L. And let's see that this is indeed the case. So now we're looking at L1, L2, and E. Are these three clauses strong enough to imply L that you see here at the bottom? Okay, and the answer is yes, because x equal to 1 removes this part here, and then you're left with y is different than 1, and y is between 1 and 100, which clearly implies that y is between 2 and 100. Okay? So basically, this explanation clause E, in a sense, represents the original constraint for the purpose of implying L. Okay? So this is the explanation clause. Let's look at the second example. Suppose that our constraint is x smaller or equal than y. So let's take a minute to look at this rule. Okay, what does it basically say? So give it a constant m, and what it says is that x is smaller or equal than m, or y is bigger than m. And this is clearly true if x is smaller or equal than y. Again, let's take an example. Suppose that m is equal to 7, and suppose that the consequent is false. If the consequent is false, it means that x is bigger than 7, and y is smaller than 7, smaller or equal than 7, which is clearly impossible if the premise holds. So this is, again, it's a sound inference rule. So again, let's continue with this rule, and again, look at an example. So suppose that we have the first literal is L1, as you can see here, and L2, that y is in the range 0 to 2. And we have the constraint that x is smaller or equal than y. But if x is smaller or equal than y, then x cannot be 3, right? Because y is not more than 2. This is why x has to be in the range 1 to 2. However, this is still a general constraint, and what we want is an explanation clause. So let's instantiate the rule that we saw in the previous slide. In this case, we instantiated the rule with the value 2. So here, x is either smaller or equal than 2 or greater or equal than 3. And indeed, this is an explanation clause according to our definition. Again, this is trivially implied, well, not trivially, but we already saw that the rule is sound, so therefore E is implied by C. And let's just verify that it is strong enough to imply L. Well, let's look at this. So since x is between 1 and 3, and here it says that x is smaller or equal than 2, then this becomes false. If this becomes false, then y has to be at least 3. I'm sorry, I had to go to the other direction. Sorry about that. Sorry. So y is between 0 and 2, and together with the literal here that y is greater or equal than 3, these two, this makes this part of the disjunction false, and what we're left with is that x is smaller or equal than 2, and this is what is the literal L. This is what is implied here. So we see that E is strong enough to imply the literal that the original constraint implied. So far, okay? Any questions? Okay. So let's continue. So how does PCS instantiate the rules? Well, for every rule, there is a way, looking at what was implied, there is a way to infer what the constants should be. For example, in the last example that we saw, we took m to be the maximal value of the domain of y. And perhaps a hint to what I'm going to talk about a little bit later, we have some freedom in choosing those values. And in fact, we can make a stronger inference and learn stronger facts by playing with these constants. Okay, we're going to talk about this a little bit later, provided there is time. Okay, so we saw the explanation clauses for 2 rules, but as you can see here, for each rule, there is a way to derive such an explanation clause. So this table lists some of the famous constraints we have. In the longer version of the article, we have a longer list of such an explanation clause. So as you can see, each of these rules is parameterized by constants. Okay, so remember we saw this diagram before that showed that this is how a proof looks like. So for example, if you have inequality, then we just instantiate the rule, we produce an explanation clause, and we continue from there through sign resolution all the way down to the empty clause. Just a small comment. So far, we did not consider the Boolean structure of the formula, but this is not a serious problem, because once we have a disjunction, all these rules work as well. So for example, if you have a disjunction b or x smaller or equal than y, you can still infer from this b or the original explanation. So this works well enough in this context as well. Let's look at the architecture of PCS. So as I mentioned, the architecture resembles very tightly the way that modern CTCL Subsolvers work. You just start with constraint propagation. So if you're familiar with a similar diagram from SAT, what you will have here is BCP for Boolean constraint propagation. So if this propagation ended well without a conflict, then you just go ahead and make a decision for a variable that did not have a value so far. If it happens to be that all the variables have a value, then you're done. The formula is satisfiable. Otherwise, you go back to constraint propagation with the new value. And suppose that you actually hit a conflict, then you analyze this conflict. If it happens to be that the conflict occurred at decision level 0, which means that it does not depend on any decision, then you're done, because the formula, you just discovered a contradiction. Otherwise, you compute a backtrack level and you go back to constraint propagation. So this is, anybody who's familiar with CTCL knows that this is the basic structure of how Subsolvers work these days. So the structure here is really very similar to what Subsolvers do. So as I mentioned, it is inspired by modern Subsolvers. The learning mechanism is used for constructing resolution proof. And I will now go over how this learning occurs and how analyzed conflict works. Eugene, do I understand correctly that I don't have any more time?
You're just about out of time, right? Just a couple of minutes.
Yeah, okay, so this is actually, yeah, so I actually did not plan the time well. So I'm going to actually skip a long part here because I'm out of time. So describing how analyzed conflict works, I'm just going to go all the way to the end. So there are several optimizations here that are somewhat interesting. So if you're interested, those slides are available, of course. I will just mention a little bit about where it is today. So in 2011, it was competitive with what used to be back then the leading CSP solver, which was Mistral back then. It was about, it had similar results. And this is the original future work slide from 10 years ago. So what you see here in orange is the updates. So back then we talked about non-clausal conflict analysis, which means that you're going to learn not necessarily signed clauses, but general constraints. And indeed, this was another work we did, and we published this several years ago in JER. We also talked about interpolation, and indeed, PCS or HCSP, the way it's called now, is supports interpolation. And then in terms of performance, so the follow-up on PCS, the next generation of PCS, which is called HCSP, won 2 gold and 1 silver medal in the Mini-Z Challenge of 2016. So it's also a very competitive solver. So to summarize, it's a cool CSP solver. It's competitive. even more than what it says here, and it produces machine checkable proofs. And the hope is that indeed people will start finding case studies, finding a usage for these proofs and for the course. So I will conclude here.